Hey, good morning, everybody. First of all, can y'all see my screen?
Yes, ma'am.
All right, perfect. Okay. Well, hey, I'm Dawn Hayes. I'm happy to be here. Definitely thank you to Steve and to NSI for letting me talk to you a little bit about pretty much my favorite thing ever, depositional environments in sedimentary rocks. So we are going to start with a little bit of an overview of some of the things that go into our models that are very impacted and can be heavily impacted by the depositional environment. So we're going to focus on influences of the depositional context on reservoir and completions models. And I will, like Steve said, be using a lot of examples from Permian Basin unconventional reservoirs. The reason that I chose this lovely image slide is I think it's a really nice modern analog for the depositional systems that I'm going to be talking about today, where we have sediment gravity flows coming into a deeper basin from a shelf. So this is, you can see there's mountains in the background here. We have a nice shelf here that's relatively shallow. We have sediments coming off of the shelf in various places. Over here, you can see the sediments coming out into the basin in these fans, and they're pretty low angles, so not a very steep slope here. Over here, though, we see an extremely steep slope and not much sediment coming off of that portion of it, except for right over here, where we have a slump here down at the base of it that hasn't traveled very far from the slope. And then, of course, we have over here some erosion. We have a fan out here on the seafloor with a big canyon actually being eroded through it. And then, of course, there's things in between that represent a little more quiet deposition on the seafloor. So I thought this was a great analog. If you're interested in looking it up, it is off the coast of Southern California. So why did I want to focus on Permian unconventionals? Well, first of all, because sedimentologically, I think they are one of the most interesting depositional systems, definitely the most interesting unconventional depositional system I've worked with, but they're also really important for production. The Permian in general is the largest oil producing basin in the US. It has been since the 1950s. Production, though, has increased tremendously as unconventional plays have become dominant there. And the drilling and completions technology, of course, just continues to improve. And these two figures kind of show that. We have one that's just showing the difference between the year 2000 and 2015 with 4 of the major unconventional plays I'll be talking about today: Wolfcamp, Sprayberry, and Bone Spring in both the Midland Basin and Delaware Basin portions of the Permian. Also, since 2015, as everybody who is familiar with the basin might know, there has been a really, really large increase in production and in the productivity of new wells coming on. And almost all of those are horizontal, hydraulically fractured in these unconventional plays. So super important basin, currently producing 43% of US crude oil and 17% of natural gas. So those are some of the reasons I'm focusing on this one. And okay, just a quick overview of some of the geologic inputs in models that I'll be discussing today that are, I guess, depositionally mediated. These are going to vary based on your depositional setting. Of course, we're all familiar with permeability and porosity varying by rock type. We'll talk a little bit about that, but also how the rock types are naturally distributed in reservoirs, both vertically and horizontally. And then mechanical properties, of course. We'll talk about variations because of mineralogy and rock type, and potentially connections between those things and fractures. Layering within the reservoir is definitely one of the, I guess, most important things that is mediated by deposition. So what are the basic mineralogy differences in your units that you're putting into the model? Are they depositionally distinct? Are they formed from really different types of processes? Can you separate them into distinct units? What do the vertical stacking patterns look like? You know, how thick are the beds and how do they change? And then, of course, the lateral continuity or geometry and shape of those units is really important in our models. And then, of course, fluid properties can vary by different rock types. So our oil and gas gravity can vary. Some of our other elemental concentrations can vary. Our formation water composition and the volume that'll be produced is sometimes extremely different between two different thin depositional units right next to each other. So I'll touch on a few of those things with examples from the Permian Basin. Won't get to everything, but I will get through as much as I can. If we're going to talk about the Permian and we're going to talk about these unconventional reservoirs, where we're going to focus on deposition between about 299 and 272 million years ago. And this is a nice little diagram of the strata deposited during this time. These again are those major unconventional plays, the Wolfcamp, the Bone Spring, the Dean, and the Sprayberry units, if you've heard of those ones. And on the far right here, you can see sea level changes at two frequencies. One is really, really long term, and the other one is the very high frequency one. So just a couple of things to mention. Down here at the Pennsylvania and Permian boundary, at the very beginning of this period, we have a maximum glaciation, very low sea level. Throughout the Wolfcampian and deposition of what operators call the Wolfcamp, we have a gradual sea level rise with a lot of small fluctuations, followed by right here, a big drop in sea level that's called, or I guess in the stratigraphy, it's recorded as the middle Wolfcamp unconformity. So we've got a little erosive contact there. So glaciation begins in the last part of the Wolfcampian to wane just a little bit, but you still get these big swings back and forth on a higher frequency sea level scale. Once we get up into this period here, Leonardian, we start seeing a really gradual sea level fall with lots of sharp drops and rises here and here, here and here. And those really control what's going into the basin. They're very important. So we'll focus on that a little bit in the next couple of slides. So where is this? For those of you who aren't familiar with it, Permian Basin in the US is kind of here in the southwestern to central US, in the southeastern part of New Mexico and the western part of Texas. Here's a paleogeographic figure of what that looked like earlier in the period when the Wolfcampian sediments were being deposited, and then later in the Leonardian. The big influence I think we would want to point out is there is a continental collision going on right down here. So a lot of tectonic activity and uplift here, and erosion of sediments and shedding of those into the basin. Also, I should mention some potential volcanic activity. So like in other basins, the Permian does have some ash layers that are pretty continuous across parts of the basin, and they're coming from this continental collision here. Although in the Permian, they are typically very thin and don't cause drilling and completions hazards. So basins themselves, we can separate the Permian Basin into these two here, the Delaware and the Midland. They are both intertectonic marine subbasins. They're rimmed by carbonate platforms on the outsides here, as you can see, and the outsides here, as you can see. They're relatively deep water, though, in the center of the basin, so 500 to 2,000 feet, so below influences of storms and things like that. Their sediment gravity flows, just like in the image at the beginning that was showed. So they're coming into the basin under the influence of gravity. And of course, the sea level and climate changes definitely determine the type of sediments. And you can kind of see that difference here. If you look at early Wolfcampian versus later in the Leonardian, we have differences in paleogeography and a little bit of a difference in sea level. So what does the present day structure look like here? It's actually not hugely different than it was back 299 million years ago. The Delaware Basin over here on this side is still much deeper than the Midland Basin and has a much steeper basin margin here than it does on the western side. And the Midland Basin is still a bit more of a shallow, like gentle sloping basin, except for this little portion of it right here. The purple or pink line here that I'm showing is just the top of that Wolfcamp formation. So you can trace that across the basin. A couple of things to note. One is that there are variations in thickness, and you can probably see, if you squint your eyes a little bit, variations within this unit. It's not just one big thick unit of the same thing. There's a lot of little lenses of sediment in there. You'll probably also notice everything gets very complicated once you get up against the margins here of the Central Basin platform. So that's just something to look out for. That's where the stratigraphy gets tricky, and there's also a lot of faulting. So I mentioned sea level. I guess an easy way to explain this is just to go through this diagram very quickly. In the Permian, there are sea level cycles influencing what sediment gets into the basin. When sea level is relatively low, we get a lot of land-derived sediments coming across the shelf and getting out into the basin in the form of big basin floor fans that can spread out and go out into the basin for miles. If we drop our sea level in a time like this, we're going to get sediments coming out farther and farther and farther into the basin. If we have a higher sea level, those carbonate platforms get flooded on the shelf here, and carbonates start to build. So when climate is warm and sea level is higher, those carbonates are very, very happy, I guess we'd say, and they aggrade, and that prevents the siliciclastic sediment from land getting across the basin. So what we get during those times of higher sea level is mostly carbonate derived from the platforms, and those sediments get into the basin the same way, sediment gravity flows. Occasionally, you get really big debris flows coming in. These are pretty important in the Permian, especially in Wolfcampian and Leonardian time in these unconventional reservoirs. And that happens when you get a piece of the edge of that carbonate platform actually breaking off very quickly, mixing with a bunch of other sediment and sliding down slope. And these can reach far out into the basin, but they can also stack up right here next to the platform, as you might imagine if you have a pretty steep platform. So that's just a really quick overview of how sea level changing a little bit during this time back and forth is going to give us different types of sediment during different sea levels. So what types of sediment? We have a lot of carbonates from those platforms, as you might imagine. So here's some photos here of these beautiful carbonates. You can see large macrofossils in there, a lot of very large carbonate clasts in these, and those are mixed up with carbonate mud and with a little bit of silt sometimes, and then also with a little bit of organic matter and potentially clay. And that all mixes up and is transported in the same sediment gravity flow. These tend to be, when they're really coarse grained like this, a more cohesive or plastic flow. So those form what we call debrites. They don't have a lot of fluid in them. They kind of stick together. If you can imagine a sediment that's it has a lot of large clasts in it, but it's relatively muddy and it stays together as it travels down slope. Very different than that are our turbidity currents. If you've heard of turbidites, you've probably seen photos like this one on the right and this one down here. In the Permian Basin, the turbidity flows can be either carbonate dominated, so very small carbonate grains, or silty and sandy, like the ones that are shown here, and they might have structures in them like these do, things like rip-up clasts or ripples, laminations. And then, of course, in places where you're not getting big sediment gravity flows into the basin, or you're only getting the very, very tip of those sediment gravity flows, you get a lot of mud rock accumulation like these show down here. And this is just a thin section image zooming in on a microfossil here. So the mud rock dominated successions are usually a mix of clay, a little bit of silt, a lot of organic material, and a lot of microfossils. This diagram I like because it shows some end members of what the sediment gravity flows look like in the Permian. Everything from thin, low density turbidites all the way to those big whopping debrites with the giant clasts that I showed on the last screen. The low density turbidites tend to be dominated by fluid, so lots of water, very little sediment. And they, in the Permian Basin, tend to be relatively thin compared to some of the debrites, especially in the carbonates. And those have some key sedimentary structures that allow you to identify them in core. High density turbidites are not quite as common out in the center of the basin, but as you go towards the edges of the basin, these do become more common. And there's also something that's really interesting called hybrid event beds, or HEBs, in parts of the Delaware Basin These are kind of a, I guess you can imagine, a mixture between something that has more fluid flow dominating it and something that has a more cohesive flow dominating it, because it's all on a spectrum. Not always easy to separate, but they form these beds it's in the Delaware Basin that usually look a lot like this one here at the top. Some people call them linked debrites. They will have the coarse grain material at the base, and then the finer grain material with a lot of soft sediment deformation and kind of folding of sediments, and they grade upward into really muddy sediments. Over on the right is a beautiful example of that from the northern Delaware Basin in the Wolf Camp. You can see in this one, carbonate sediment, coarser grained at the bottom, and then we have a silty carbonate here with a lot of shearing and dewatering structures, and then that grades upward into finer and finer grained stuff that has in here plant fragments, but also a lot of more marine organic matter. Something definitely to note, the porosity trend in these carbonate dominated hybrid event beds is opposite of what you would expect in a sandy one. So although the clay increase upward is about the same, and our TOC increase upward is about the same, our porosity is the opposite. These actually up here in this section, these have higher porosity than you find in the more carbonate rich coarser grain portion below. So how do these look on a larger scale? This is really important. Whether we're, in some cases, they're varying at the larger scale on the order of, let's say, like within a mile, they change laterally, and sometimes it takes several miles before they change laterally. But really big bottom line is they don't look like perfect layer cake. The sediments in this basin definitely have some interesting stacking patterns. This image at the top is really nice example from Delaware Basin Wolf Camp, where we're just showing a little block diagram of the edge of the shelf right here, and our sediment gravity flow fans coming out in the basin. These are grain dominated deposits, but you can see there's a lot of mud in between. And then there is a debris flow deposit here reaching way out into the basin. Just to be clear, these sediment gravity flows in the Permian Basin can reach out into the basin for miles. They can be really, really laterally extensive, and you can trace them for long distances in some cases, but they do tend to be thicker and less laterally continuous, like in this picture right here. See all these small ones here nestled up against the shelf, but as we go out into the basin, they thin. So up against the margins of the basin, they're a little bit more complicated. They tend to be thicker, they tend to be less laterally continuous, and sometimes they stack. And so they look like one big unit, but they're actually several smaller ones all stacked on top of each other. This is a great example over here at the right of what that would look like in cross section if you could look through the Bone Spring, one of those unconventional reservoirs. The sandstones are definitely thinner and less continuous than our carbonates. Here, our carbonates are probably composed of lots of stacks of what we have over here in this section here, and those stacks of carbonates thin over in this direction. So just a little picture of, if you're looking at this in cross section, how all those units might vary across a relatively small distance. So this would be a distance, I think probably average distance here in this cross section, we're just going from one county to another. So, maybe about 50 miles or so. So those carbonates don't look exactly the same all the way throughout. They are definitely variable based on where in that part of the depositional system you are. So where in the fan? Are you in the middle of the fan where it's high energy? Are you a little farther out? Are you way out on the fringes? Or are you in a completely separate depositional environment and you're on the next fan over? So a great example is, I guess, of a fan that's not very fan shaped, it's definitely more elongate, is this one from the Wolf Camp in the Delaware Basin. This fan, as you can see, has an axis trending in this direction, and we have a lot more carbonate here along the axis than we do off the axis here in this direction and in this direction. Something to note, the carbonate percentage changes really quickly in across the fan in this direction, but it changes a little less quickly if you're going across the fan in this direction. So something to consider. The fans won't always be nice and symmetrical. In a lot of cases, especially the carbonate ones, they can be elongate in parts of the basin, representing a point source of sediment that keeps coming in that same area, kind of being funneled in. So the amount of carbonate changes, but it's not just the amount of carbonate that changes from one part of the fan to the other. It's actually the type of sediment. So if you were to go and take a core, which these guys in this study did, from different parts of the fan, you would find very different rock types. So this example, let's go with this one right here. The one that's from the middle of the fan, so probably the highest energy portion, you can see this carbonate deborite has tons of big clasts in it. It has big mud rock clasts, it has big carbonate rock fragments, it has a lot of fossils. Very thick deposit. And this is characteristic of what you would find building up in the center of that fan. If you go off the axis of the fan a little bit, kind of laterally in this direction, you would see that, yeah, you still have a lot of carbonate. So you've got this big carbonate section here, but the clasts and the fossils, all the fragments in it are not as big. It's not quite as high energy of a deposit. So smaller carbonate particles and not as chaotic, a little bit more well sorted. And then if you go way off of the fan out here towards the basin, you see something very different, still relatively high amount of carbonate, but you see a lot of thinner interbedded carbonate mud rocks. The large clasts are kind of confined to really thin layers here. So we see a very different rock type depending where we are on these fans. And as you can see from their little core description outlines here, you don't have to know what that means, but they're different rock types in this section, which is stratigraphically equivalent to this one, which is stratigraphically equivalent to this one. So we can have some big differences over a short distance. You can also have a lot of big differences vertically. This is one example of that from a Wolfkamp play. In this example, the question was, how do we represent that vertical heterogeneity and then trace it laterally? So a really simple approach here would be to use wireline logs and create a petrofacies model based on that, and then test that by actually going to the cores and describing the depositional facies you see in the cores, and figure out which of your models matches your, I guess, geologic reality the best. And you can assign the properties. In this case, it was permeability and water saturation, or mechanical properties here. You can assign those to the different facies and then use those as layers in your model and propagate that to other wells with the same logs. There's also definitely, you can imagine, many ways to model these facies. One more sophisticated approach to representing that vertical and lateral heterogeneity is shown here. I'm not going to get into details on it, but I think everybody should know that next week you will get details on this. So please tune in next week if you want to hear a little bit more about this. The cross section at the top is showing what's called a geofacies cross section. And you can see here we have shallower carbonates in one part of this basin, and that transitions very quickly into mudstone dominated rocks. So in the machine learning facies approach, we can actually decouple the domain specific facies from their log signature. So you can look separately or investigate the interactions between your reservoir quality facies, which is what happens in the pores, your geofacies, which is shown here, which is representing the rock as far as mineralogy concerns. You can see the mineralogy differences in those facies, and then also the geomechanical facies. So if you combine all three, you can put those into a 3D geo model. And again, tune in next week for more about that. It wouldn't be a fun presentation if I didn't show some really interesting variations in the rocks that you might see based on depositional environment. These are some things you might not see on basic wireline logs, but you can predict them if you have a good depositional environment model. In A, B, and C here, we have three rocks that are probably approximately the same mineralogy, but they have very different fabrics, as you can see. One of them is very nicely finely planar laminated. The other one is really convoluted, and this one is convoluted as well, but has large chips of mud rock in the siltstone. So these can definitely behave differently when it comes to porosity, permeability, and mechanics. Another example of A little surprise that you might see every once in a while in Permian Basin unconventional deposits, especially near the slope, is slumps. So often slumped intervals occur, and you can imagine if you cored through one of these or drilled a well through one of these, you're going to see all kinds of crazy things, and you'll see that the geometry of the sediments is folded typically or completely intermixed. And that definitely makes for different reservoir quality than you would find in something that was not slumped. The example at the bottom is just showing the influence of burrowing. Here's a typical mud rock from the Wolf Camp with no burrows in it, and here's one with burrows in it. These ones without burrows tend to have a little bit higher TOC and maybe some higher clay volumes. These ones here with the burrows in them tend to have slightly lower TOC, and they also have typically a lot of silica cements in there. I'll talk about that in just a minute in the next, or sorry, in 2 examples from now. This is an example I like to show because it's something we typically think, okay, well, if we have more carbonate in our mud rocks, they're going to have higher rock strength. And if we have more clay, it's going to affect it negatively. So we kind of want to find that sweet spot. So both of these examples show that kind of trend. More clay, less carbonate, lower rock strength. We see that here, we see that here too. And they're both from relatively deep settings, depositionally, and they're both in epicontinental basins. But the example up here, in this particular depositional environment, the high clay facies are deposited in the shallowest environment, and the carbonate-rich ones are in the deepest environment. In this one, it's exactly the opposite. We have more clay in the more distal depositional environments and a lot more carbonates in the other. So it's a great example of just knowing a little bit about the depositional history of your basin can allow you to really quickly predict your mineralogy changes and the mechanical properties. But you don't want to get it mixed up. They can be opposite depending completely on the depositional environment. Something else that can differ a little bit that definitely impacts our pore networks and mechanical properties is the type of quartz that we see in our mud rocks. The quartz morphology in the Permian varies, and this can make your rock more chert-like or more claystone-like, and it can also influence the pore networks. On the left, I have a couple of diagrams showing, let's see, our zirconium versus silicon dioxide here and here. These are sized by the percentage of titanium. Essentially what these diagrams do is provide a nice little proxy for the quartz that is more likely to tridal up here, so coming from those land sources, and then our other quartz that is biogenic or authogenic, that's coming from microfossils that are in the rock and have been dissolved and reprecipitated in a lot of cases. And those usually are things like radiolarians or sponge spicules that are really, really silica rich. Over at the right, we have beautiful SCM images of what these look like at the very, very fine scale and how they impact the rock properties. So here, all of the red that you see here is quartz, and this is really tiny microcrystalline quartz. If we zoom in, you can see all of those individual little blobs of quartz or crystals. And if we zoom in even more, you can see the quartz crystals up close and that there is a lot of interconnected porosity between them. That can definitely be a good thing. If you're looking at some of these rocks and you think, oh, well, it's tight rock, it has a lot of silica, mechanically that's nice, but they can also have a very nice interconnected, small, tiny pore network and can have increased effective porosity because of that. And something that can impact those really fine scale properties also is the redox conditions within the basin. So in other words, how well oxygenated is your basin? If it's better oxygenated, you probably wouldn't expect to preserve as much total organic carbon. We also sometimes think about, okay, well, how does the oxygenation level and the carbon preservation change with water depth? Or other factors. A lot of things can influence that, climate or nutrients in the primary productivity of the microorganisms in the water column, or whether or not the basin is getting nice circulation from the open oceans or whether it's a little bit more restricted. So these things can be linked to depositional setting, but they won't always be. They actually can vary independently of that, at least to some extent. And that's important. That's why I'm putting out this example. This is from one well in the Midland Basin and Wolfcamp Formation. But it illustrates a trend that I've seen in areas throughout the rest of the Midland Basin and in a lot of Delaware Basin cores as well. So average TOC, if you compare the upper part versus the lower part of the reservoir, definitely much higher in the Wolfcamp A. And if you compare all of the redox sensitive trace elements, things like nickel, molybdenum, vanadium, uranium, copper, they show this trend where they stay relatively low throughout Wolfcamp B time, and then they really increase on average and have a lot of really high spikes here during Wolfcamp A time. So that's signaling that we might have a change in redox conditions from Wolfcamp B time to Wolfcamp A, and that also in Wolfcamp A, we've got a lot of high frequency fluctuations. Something that is interesting about that, as far as the photos on the right, well, these high frequency fluctuations in the redox conditions sometimes can lead to preservation of organic matter. Sometimes there's a lot. This is a beautiful example of a lot of organic matter incorporated into a mud rock, but it doesn't have any porosity in it. That's going to depend on the maturity of your reservoir. This one here, however, is from a part of the basin that is relatively high maturity, and that porosity it can be pretty significant. In the Wolfcamp, it is usually not the dominant type, usually interparticle is in these really tight mud rocks, but the organic matter porosity can contribute a significant portion of that. So why the zircon silicon ratio? Well, as I mentioned in the last slide, that can vary based on your detrital input. And you might think that, okay, I'm getting more detrital input, like in this diagram here, with turbidity flows or debris flows coming in. If I get more detrital input, that means I am probably shallower, right? Or I'm getting more oxygen into the basin. But it doesn't always have to be that way. Like I mentioned earlier, it's not only the depositional environment, it's you can see these chemocline diagrams. The chemistry of the water in the basin can change. So maybe during Wolfcamp A, we might have had that, I guess, line of chemical change a little bit higher, so that more of the basin was more disoxic to anoxic during short periods. Whereas in this example here, Wolfcamp B, we may have had a lot more deep basin deposits and not as much terrigenous or silt material coming into the basin, but we didn't have anoxia to dysoxia in as much of the basin. So I like to show this example because it's counterintuitive. It's complicated, which makes it definitely interesting. So you see a relationship that you might not expect, but it's pretty important because it determines how much organic material you have in these sediments, and then also some of their mechanical properties that have to do with the type of silica and how it's distributed. Okay, and we're going to end with this. It all starts with deposition, so we're going to end with deposition 2. I wanted to show the diagram on the left because it compares different U.S. unconventional plays with respect to their, I guess, complexity, we'd say. Compositional, textural variability, mechanical variability. So as you go in this direction to the right, to the Wolfcamp, which is in the Permian, and that's most of the examples that I discussed today, you're getting more and more heterogeneous rock, and the porosity, permeability, and rock mechanics within those particular rocks, that's going to be a lot more variable. But I did want everyone to remember, when it comes to deposition, a little bit of context can go a long way. These sediments might be complicated and difficult to model, but they're certainly not impossible. So depositional context can usually explain a lot about reservoir behavior, and incorporating it into our models sooner or later, I think, is probably the best way to go. And with that, I want to have time for questions. So if you guys have questions,
leave it on that last slide, or you can leave it here, whatever. I think it's no, go back to the other slide. I just love that Southern California picture.
Yeah, that's a beautiful image.
And, you know, I've been writing down a bunch of questions here. And first, for our audience, I'll say that I think a lot of people feel like they've been drinking from the fire hose this morning.
Sorry about that.
Which is great, because this is recorded and you can go back and you know, refresh your mind on some of this. But one thing that jumped out at me real quickly is, I'm not sure I ever heard you use the word shale.
Mm-mm.
And, you know, we all talk about the shale revolution and stuff, and my phrase is grunge rock. And I think that's what you showed us today, was a variety of grunge rock.
Yes, all different kinds of rocks. Yeah, so a lot of sedimentologists won't use the term shale. We'll call it mud rock instead, or you know, preferring to not call everything shale, just because of it's like a terminology thing that has to do with the fissile nature of it. And so not all of our mud rocks are fissile, especially the ones with tons of carbonate and silica. So we just call them mud rocks. But yes. Yeah. Grunge rock. And in the Permian, that's not just mud rocks. I mean, that's silty things, and that's really carbonate rich rocks too.
I think for our completions audience, what's really important here is what you showed about the significant lateral heterogeneity as well as significant vertical heterogeneity. And, you know, on a small scale, like when you're designing a single fracture, the layer cake concept is, you know, reasonably okay.
It usually will work.
Once you get beyond the scale of a single fracture, that model starts to fall apart really quickly, I think.
Yes. And, you know, even within a single well model, in formations like this that are really heterogeneous, your rock properties in those really thin layers can be completely different. And you can even have completely different fluids in the different layers. And I don't know, I mean, I would think if you want to model that more realistically, you'd probably want to know the proportions of each of those sedimentary layers in your formation, or at least have an estimate to populate the model with the correct proportion.
I think the other thing, you know, in the Permian, you know, with its geologic complexity, and, you know, and again, for our international audience, especially, you know, each of these basins is different. And as Dawn showed, you've got like the Haynesville gas basin that's relatively, you know, easy to model. The Marcellus, you know, geologically, depositionally, not so difficult, but you got to lay on top of it all the folding and faulting that happens due to the Appalachian uplift. So it gets more complicated. And, you know, how that applies to a reservoir you might be looking at in the Middle East or something that's, you know, classified as an unconventional, you know, they're all going to be their own animal. And you have to step back and understand, as Dawn said, I think she said it really well, that a little bit of depositional context goes a long way to helping you as an engineer understand what do you need to focus on, and how do you need to build that up into, again, into a geologic model that you can then feed into, you know, use as a repository for feeding into your engineering models, which is something we'll get to in a couple of weeks when we have Katie and Dario in 2 weeks from now. So, you know, Dawn, we got a couple of questions coming in from the audience here instead of just sticking with all my questions. So is there a correlation, from Michael, is there a correlation in terms of the amount of gas and oil that can be extracted? And I'm trying to paraphrase this a little bit. You know, how do you and we're kind of jumping ahead here, Michael, because we're actually, when we get into doing real geologic modeling, we're going to show something called a productivity index or productivity quality of these. And so, Michael, your question, I'm going to actually, now that I read it better, is something to sit on for 2 weeks, because it's really, that question really leads into what we're going to do with more sophisticated geomodeling. Let's see. Oh, here's a good question from Darby. For the Permian and the Midland basins, would you consider these basins to be data rich or data poor? And if you were going to recommend to a client what additional data sets they should capture to improve their production output, their completion, development, production output?
So I think both of these basins would probably be considered pretty data rich. And I guess the only caveat to that is that in areas where there haven't been a lot of wells yet, then they're not going to be. So there are hot spots that are extremely data rich, amazing amounts of data.
But I think the point is, because of the complexity, you need a lot more data than you might in, say, the Haynesville, because you've got, county by county thing, or well, even smaller than that. Texas counties are huge. Section by section, you've got a lot of things varying. So you really do need a lot of granularity in the data to understand what's going on subsurface.
True, yes. And I think so. The farther you are out into the center of the basin, the more homogeneous things are going to be. But as you go out from there, even a little bit, you do start to see more variability, and you would need more data to characterize that. A lot of companies that I've worked with in the Permian are doing that by, long ago, they took cores and they have a lot of information on those cores, and now they're using high resolution mineralogy on cuttings to extrapolate back and correlate with the cores, and basically matching that elemental data back to their rock properties that they have from their core measurements and trying to tie that in. I think the other thing that people can do, and I think a lot of people don't do it, is look at wireline logs from more than just the little postage stamp that you're working. Sometimes if you get that zoomed in, you're really not going to see all the differences. If you zoom out and go for the whole basin, I mean, I know you don't have time to map everything, but for basins like this that are more complicated, a little zooming out on your mapping is, it can be a big deal. That can give you a different perspective.
Again, Dawn, I think the phrase you made of a little context goes a long way. And understanding where you are in the bigger picture, I think that's a great way to think about it. And with that, we're kind of zooming in on this has gone very quickly. We're almost up at the end of the hour. And Dawn, thank you very much for doing our first of our series on intro to basin geology. And I'll make kind of a closing comment for everybody that, again, this is, the Permian Basin is the most important unconventional basin in the world. And so this really focused in on that. But each of these depositional basins is their own animal. This is a marine deposition. As Dawn said, the influence of ash deposits, volcanic deposits in this basin are very, very limited, where in other basins like the Eagle Ford, they can be significant for completion operations. And so each basin is its own animal. In one session, there's no way we can touch on all that, but it's having a basin expert like Dawn at your available to you can save you from a whole lot of problems. as you get into, doing your engineering and your completion. So Dawn, thank you very much for that. And
You're welcome. Thank you, guys.
I'm gonna take control back of the screen here.
All righty.
Yeah, I think if I can do this correctly. There we go. I'm getting better at this. Maybe. I thought I was getting better at doing this, controlling the screen thing. Here we go. So next week, as Dawn mentioned, we're going to take a dive into petrophysics and how that can be used as the base, how petrophysics is used as the basis for geomodeling. And then a particular with Dave talking about machine learning, artificial intelligence, applying that to petrophysics information to then feed the geomodel to extend it beyond what the normal inputs that you would have. And I think the work Dave's been doing with Yulia is very exciting. It's, everybody likes to learn about the cutting edge stuff. Now that Dawn has given us kind of a basis in the reality of the world, now we can go off and probe around in some of this, very new, apply the science to the observations. And so I'm really excited about next week's. And then following that, we'll take all of these disparate data and start feeding them into a massive geomodel and show how that's used to create opportunities to optimize engineering and operations. So with that, we really, look forward to seeing everybody next week. And I hope these geologic sessions people find them useful. I think they're a lot of fun. And again, as I said, if anybody's interested in being a guest speaker, just let us know. We'd love to get you in the program. So with that, again, thank you, Don. We're a little over time, but thanks for your efforts. And I owe you one of our beautiful NSI limited edition Frack Everything coffee mugs. So next time I'm in Midland, I'll bring a coffee mug with me. Okay.
Awesome. Can't wait. Thank you, everyone.
Okay. Bye-bye, everybody.